Ahora voy a presentar el último panel antes de la
I'm going
comida.
to present you the last panel before lunch. Jason Pontin is going to talk again, and we're going to talk more about energy, but about the challenges of electric grids in the future. Jason Pontin, welcome on stage again.
Yes, I will. They're giving some instructions on the fly. The great moral challenge of our age, the civilizational challenge, is climate change. And yet, though we know that almost all of the observable climate change is the result of industrial emissions, we have very little plan for, or very little idea about how to create a sustainable energy future. Today, less than 2% of worldwide energy output derives from advanced renewable sources, such as wind, solar, and the like. Less than 2%, and the reason is almost wholly cost. Could someone adjust my thing, please, so I don't deafen the audience? Could someone adjust my mic? I will hold it and speak like this until they adjust it. Less than 2% of worldwide energy output derives from alternatives, and the reason is almost wholly cost. Petroleum is more expensive than any alternative. Petroleum and coal. Now you can hear me? Fine. Petroleum and coal are simply cheaper than any of the existing alternatives. It's not an easy problem to fix. There are complexities with the energy generation. There are unsolved difficulties with storage. And even our grid, which is essentially an industrial grid created in the 19th century to serve energy needs. And even our grid, which was created in the 19th century to serve 19th century industrial needs, isn't sufficiently sophisticated. It isn't sufficiently smart to manage the fluctuations of give and take that we'd expect from an alternative, from a truly modern electrical grid. So, my next speaker, John Kassakian, who is a professor of electrical and engineering and computer science at MIT, is going to show you how different a truly smart grid would look like, take you through some of the difficulties of creating such a grid, and paint you a future about what the benefits would be. And after he's delivered his keynote address, I'm going to come up on stage and have a fireside chat with him. Ladies and gentlemen, Professor John Kassakian.
Gracias, Jason. And buenos dias. And that's the extent of my Spanish. Everything that we have heard so far today, which has been fascinating, wouldn't be possible without electricity. We take electricity for granted. We plug something into the wall, we expect it to work. If we plug something into the wall and nothing happens, first we're surprised, then we're disappointed, then we're inconvenienced, and then we're angry. Except for clean water, there's no part of our infrastructure which is more critical to our well-being and quality of life than electricity. I'm going to share with you some vision of the electricity grid of the future and talk about some of the challenges and perhaps some of the technologies that might be available to meet some of those challenges. So let me start by just referencing this report that was produced by the MIT Energy Initiative back in 2011. It's available to you. I co-chaired this study with my colleague from Dick Schmalensee from the Sloan School of management, so we had an engineer and an economist on this. And I recommend it because it not only describes the system and some of its challenges and some of the future technologies, but there's also a very interesting appendix for those of you who want to learn something about how the grid operates. So in some sense, it's a tutorial. So what are the demands that is going to be on the grid in the next century? Well, first of all, we need to improve reliability. Now, reliability in some parts of the world are fine. In other parts, reliability is terrible. But in general, reliability has become a bigger issue because more and more of our lives depend upon a reliable grid. As Jason mentioned, we've got to accommodate an increasing penetration of renewable energy. There's a concern now about cyber attacks and other kinds of terrorist attacks on the grid, and I don't have to tell you people from Colombia about that. The issue of how you restore the grid is a big one. Plug-in vehicles are becoming a more important part of what the future might hold, and there's a study undergoing now in the National Research Council of the U.S. National Academies looking at what the obstacles are and how to overcome them. Rate structures are important, congestion is important and becoming a bigger problem, and the issue of providing reserve capacity is one that has major economic implications. So let's take a look at a few of these. I'm not going to go into detail on all of these, but I just want to indicate to you that there are really three parts of the grid. There's the generation part, which isn't represented here, so there are really four parts of the grid. There's the generation part, there's a transmission part, there's the distribution and the customers, that's you and me, and the control center, which controls the whole operation. And we're going to take a look at a few of the technologies that will impact some of the challenges in each of these sections. Those technologies include advanced metering, synchrophasor networks, which I will explain to you shortly, something about renewable energy sources. Power electronics has become a major component of not only our daily lives, but also the operation of the grid. There's a power electronic component known as a voltage source HVDC converter, which has brought with it a brand new set of opportunities for improving the transmission network. High temperature superconducting cable in the same way. And then lastly, there's microgrids, which might have a particular implication for Colombia's problems. So let's take a look at the challenge of renewable generation. Here's a picture of what the problem really is. This is a graph of the output of all of California's wind turbines over a one-day period. Actually, it's over an 18-hour period. In 6 hours, the generation from all the wind in California went from 1 gigawatt to 0. Then it stayed at 0 for about 6 hours, and in the remaining 6 hours, it went back up to about 800 megawatts. Now, the problem here, of course, is that during the time that the wind is 0, the energy has to be supplied from someplace else. And this is the problem of intermittency or variability in a lot of renewable energy sources, in particular wind and solar. So how do we remediate this variability? Well, one of the best opportunities and the least expensive opportunity is through dynamic pricing, where you somehow provide an incentive for the load, the customer, to reduce consumption during the time when the variability is creating a problem for the grid. The advanced metering infrastructure, which is, I'm not sure how prevalent that is in Colombia, but in the US, the advanced metering infrastructure, which is the introduction of smart meters, has been very aggressive. And those meters facilitate the dynamic pricing. Storage, of course, is the ultimate solution, but storage is a very expensive but economically very expensive and economically unattractive solution to the problem. There are a number of storage mechanisms available. People think of batteries, terribly expensive and awfully large, and they don't actually hold that much energy. Pump storage is another opportunity for pump water storage is another opportunity to remediate some of the problem, but again, the sites for that are very limited. And lastly, it's to use fossil fuel that can be brought online very quickly. And this, of course, eliminates one of the major benefits of renewable resources in that once you bring a fossil fuel unit online, you're now emitting CO2. And of course, it's poor capital utilization because you're only using those gas turbines in this case when, in fact, the wind isn't blowing. Let me take a moment to tell you something about a technology that has a major implication for future reliable operation of the grid. A synchrophasor network is a network of sensors that have been located throughout the electrical network to monitor in real time and all simultaneously the condition of the network in all those locations. And then all that data is gathered together so that you have an immediate picture of exactly what's going on in the grid everywhere, all at the same time. Prior to the advent of what are known as these phasor measurement units, which are the sensors that are scattered through the network, this was an impossibility. So with this, let me give you an example here. Forget about the spaghetti on the left-hand side. I want you to just focus on the green map on the right, which is the eastern interconnect of the United States. And what you're going to see is a fault, that is a problem with the grid down in Florida. That's that little thing sticking down there. Down in Florida, and you're going to see how that problem propagates throughout the whole interconnect. And what you're seeing is a movie of the state of the network that is created by the presence of these phasor measurement units, which are all the little red dots. So I don't know how to run that movie from here. Perhaps we had a movie problem a moment ago. I hope we don't have another one. If I press this, will it? Ah, perfect. Watch the right-hand side. And what you see there in the colors is actually the variation in the frequency from 60 cycles caused by the problem down in Florida. And that is possible to see because of the presence of those phasor measurement units. So what can we do with the synchrophasor network? Well, for one thing, we can tell exactly what's going on with the network at any time, and because we can see that, we can anticipate problems and provide a solution before they become catastrophic. And let me give you one example of that. This is the 2003 blackout. This particular data comes from the 2003 blackout in the eastern part of the United States. And what it represents is a parameter in the network, that blue line down there, that is changing with time but was not observed by operators in the system. Had that change between 3 o'clock in the afternoon and 4 o'clock, that is a period of 1 hour, had that change been recognized by the operators of the system, they would have been able to take action to prevent that blackout from occurring. This kind of information would be available with a synchrophasor network. And you can see even at 4:02, when things started to become dramatic, you see the first sharp rise over there, you still have 5 minutes, 6 minutes before the whole system collapsed. And that's almost an infinite amount of time in order to take action to prevent the system from collapsing. So this kind of data provided by a synchrophasor network can prevent significant collapses of the system caused by parameters that we can see prior to the event occurring. And this is just a map of how many of these synchrophaser measurement units are now in place in the United States. Unfortunately, they're not all linked together to give you the kind of data that I just showed you. But it's a technology that has tremendous promise for the future. Another technology that is very new, the technology itself isn't new, but its application to power systems is the high-temperature superconducting cable. And the interesting thing about the high-temperature superconducting cable is that in the same size as a conventional cable, in the same ducts, in the same space, you can put a superconducting cable that will increase the capacity of that right-of-way, the capacity of that line, by a very substantial amount. What this means is that you don't have to get new right-of-ways, you don't have to dig new trenches, you don't have to put in new conduits. And it's especially valuable for large urban centers, places like New York City, where all of the cables underneath the streets of New York are approaching 100 years old. Those cables are trying to support an increasing electrical load. And the use of superconducting cables, such as this one, which is being installed in Long Island, can obviate the need for putting in new trenches, digging up streets, and so forth. This is still very new. As far as I know, this is the only cable that has been tested so far in a practical application. And the reason I show this photograph here is to illustrate that this cable is installed in some ways that are no different from the way you would install a conventional cable. It comes on a reel, you reel it off, you put it in the ground. Sounds simple, but it's really not quite that simple. But it's a practical way of installing the cable. The voltage source HVDC converter, which is, again, a power electronic device, allows the bilateral flow of DC power on cables that, on cables that have a solid core. With a conventional, this is getting a little bit esoteric, but it's a very important point. With conventional HVDC terminals, that is, the terminals that change the AC into DC, which can then be transmitted for very long distances, you cannot use a cable if you are going to have the power flow in two directions. And there's a good physical reason for that. With this particular piece of equipment, you can have power flow in two directions on the cable. You can also tap the cable, tap the DC cable, so that you can create a DC network. Now this has major implications, again, for cables in cities, for renewable energy resources which are remote from the location of the loads, which many of them are. And it's a technology that has been made possible by innovations in semiconductor devices. Plug-in vehicles, this is an interesting one. Plug-in electric vehicles are not in wide use. The total number of plug-in vehicles in the United States accounts for about 0.1% of the total vehicles, and do not create much of a problem. In the future, the hope is that these vehicles will become more significant, that they will become more popular, and so there's a concern about how they will interact with the electric power system. Well, they can interact in two ways. They can either be a problem or they can be a solution to a problem. They can be a problem if everyone is charging their vehicle at the same time and at the time that we're having a peak load condition. They can be a solution to the problem if they're charged on the off-peak hours, or if they're used as part of a demand management, demand response program, so that they can be turned on and off Their charging can be turned on and off in response to the needs of the network. So, let me bring this to Colombia. I learned a little bit about Colombia. Is that a map? That map's right side up, isn't it? Yes, yes, right. More than half of Colombia doesn't have access to reliable electricity. In fact, I think it's even more than that. I forget exactly what the percentage is. And the problem, of course, is that, from what I've been able to understand, is that trying to provide an electrical infrastructure into the remote regions of the country confronts the problem of terrorism and destruction of facilities and the infrastructure. And so there's one new technology. It's actually not a new technology, it's a new architecture that requires a new technology. And the new architecture is called a microgrid. And very simply, all a microgrid is the aggregation of a number of generating resources, solar, wind, perhaps oil, perhaps coal, perhaps gas, into a self-contained grid that is restricted in geographic reach. Now, the problem with such an architecture is that you have to be able to control all these different pieces that represent the resources in a way that creates a reliable system. Now, my own belief is that given the choice of a microgrid or a conventional interconnected network, like you have in what was the brown part of Colombia, is that if you start to put lots of parts together, the reliability is compromised in any kind of a physical system. The more parts you have, the worse off the issue of reliability is. So in the case of the microgrid, if you're to establish microgrids in a region of the country where you cannot actually provide long lines and an interconnected infrastructure, the challenge is to provide a control system that can control all of these different pieces in a reliable and efficient manner, and a system that can respond to problems with any piece in this system in a way that doesn't bring the grid down. Now, here, this picture, it has a central power plant and a bunch of other stuff. So this is a fairly large microgrid. I would think that for Colombia's needs, one might speak of a nanogrid, something much smaller than this, but something which requires the development of a control technology that enables all these different pieces to operate together reliably and efficiently. Something else that's required is better data on how the system operates. When we wrote our report, The Future of the Electric Grid, we discovered that data on how efficiently the system operates, how effectively and reliably a system operates, is very, very difficult to obtain. It's very hard to compare how the United States electrical network operates in comparison to one in Spain, for example, because the metrics that are used are different, and what gets reported are different, and whether something is considered serious or not serious has different thresholds in different countries. And even within a country like the United States, the different companies that operate the grid have different metrics and different ways of assessing reliability. And the reason why this is important is that if you're going to introduce new technology into a system, you have to have a benchmark that lets you know whether this new technology, once you introduce it, has actually produced the improvement that you anticipated. So without some baseline, you have no way of assessing that. So for the introduction of new technology, You really need to establish the metrics that allow you to evaluate it. Grid security. As I said, this is probably something that many of you here could speak to in far better and with more experience than I can. But there are really several aspects to grid security. There's operational intrusion. This is intrusion to the grid which creates a problem with how the grid is operated. That is, it will call for a breaker to open or a breaker to close or a generator to drop offline through a control system. The problem could create physical damage if the operation caused the generator to come online, for example, out of synchronism. It could cause a system to collapse. And the response to these kinds of intrusion are manifold, and there are a number of ways of addressing it. New technologies such as the synchrophaser network could give you some indication that there was a problem, an incipient problem, in time for you to correct it. Physical damage, well, physical damage is something that you're going to have to repair, but the way to prevent it is to try and prevent intrusion into the control system to begin with. And generally, the prevention is the same kind of action you would take to prevent a cybersecurity breach. Then there's a physical intrusion. This is actual physical damage being inflicted upon the system by terrorism or bad people. And there are two kinds. It can be uncoordinated and relatively limited. Somebody throws a bomb into underneath a tower on a transmission line and brings down a tower. Well, in some respects, utilities already respond to that kind of a problem. It's known as a system contingency, and they've got algorithms for how you operate the system in the event of such a problem. That's not really the major issue. The major issue would be if this were a coordinated attack, where, for example, a group of people decided to attack a half a dozen or more substations simultaneously and knock them all out, and then we have a major problem. Not sure exactly what the solution to that is. Another problem is terrorism by electromagnetic pulse. This is where you have an explosion that creates radiation which interferes basically with the electronics. So these are problems, again, that the grid is facing, challenges that the grid is facing, that requires careful thought and new technologies to deal with. So in conclusion, there are a lot of technologies available to meet these challenges in the 21st century. Cost is a major issue. Cost is a major issue in renewable energy, not only for the resources, but also for the additional resources necessary to maintain operation in the face of variability. We have to remember that electricity is a necessary commodity, and it has to be made available at a price that people can afford. Governments have a major role to play, not only in supporting the development of new technology, but also in providing incentives for the introduction of new technology. And coordination between industry and government is really essential for setting the agenda for meeting the challenges of the 21st century. So that was very brief, and I thank you very much, and I look forward to any questions.
That was great, John. Thank you. I'm sorry I deafened you earlier with my mic. I'm going to ask John a couple of questions, but I'm going to call upon the audience, so be smart. Who pays? Who pays for these improvements that you've described? Is it the grid operator? Is it the grid operator and the utility? Is it a deferred social cost that's passed on to the taxpayer?
That's a superbly smart question,
Well,
Jason.
thank you, John.
And I think it's all of the above. Ultimately, the taxpayer pays.
There was a hiss in the corner over there.
Whether development of new technology is socialized in the sense that the government will underwrite the development and deployment of new technology until it can be stand on its own 2 feet is a question for society. The whole issue of reducing emissions is a question for society. It's a big question. Should the costs be socialized? And if so, how? It's not an easy question at all, and I don't have an easy answer for you, except everyone is going to pay one way or another if we expect to maintain our society at the level of good living at which we now have it.
So, and that suggests my second question, which, and forgive me, it's a fundamental question, but I'm puzzled by it. Why is the existing grid so insufficient to our current needs?
I think that's wrong. Yeah. I don't think the grid is insufficient to our current needs. It's clearly supplying our current needs.
It's the future needs.
It's the future needs and the future growth of the grid that is the challenge.
That's why the payment question is so crucial.
Absolutely.
I heard you say, and I believe, that current storage technologies make no economic sense, but you also called it the ultimate solution. Are there any early research efforts that you find promising? Our colleague Don Sodaway at MIT has a grid company, Ambri, I think it's called, but there are many other ones.
Yeah. I don't see any storage technology at the grid scale that has the promise of being really economical.
Why is that?
Don's, I don't know enough about the economics of Don's, of Ambri's technology to know whether it might be an ultimate solution. But the problem is that storing energy is basically not an easy thing to do. Storing electric energy is not an easy thing to do. And one way of thinking about the magnitude of the problem is that if you go to think about gasoline. Yeah. If you go to a gas station and you put the nozzle into your tank and you fill your tank, the power of filling your tank is on the order of 10 megawatts. Now, it doesn't take you long to put all that energy, 10 megawatts times 1 or 2 minutes, into your tank. It gives you some idea of the difference between how much volume is required to store a megawatt hour of gasoline, which you've got in your tank. Well, you have less than, I'm sorry, you've got 10 megawatts, let's say, times 2 minutes. Okay, so you've got 20 megawatt minutes, which is something on the order, I don't know, a third of a megawatt hour or something. A battery to do that would be huge. I mean, it would be the size of the stage, and it's just impractical. And the chemistry and materials and so forth all come into play. If you look at something like, I mean, one of the neatest energy storage, electric energy storage, it's actually water storage, is a pumped storage facility. But for that, what you need is the land and the height and the reservoir and so forth. It's just very, very expensive.
I was very attracted to your suggestion about using big data analysis to manage fluctuations in demand and supply. Are there other things we could do with big data analysis on the grid?
Well, the synchrophaser network is huge data analysis. Yeah. And if we ever get to the point where we can aggregate all that data that you saw that would be coming from the 1,000 some odd phaser measurement units on that map of the US with all the red dots, if we ever get to the point where we can aggregate that data and turn it into actionable information, the grid will be unbelievably reliable compared to today.
I'll give the audience a scoop. Every year we announce 10 breakthrough technologies, and we thought synchrophase was so important. It's likely to be one of our 10 technologies for 2014. Can we take a question from the floor, please?
Got somebody over here.
There's a gentleman here waving his hand.
And there's one back there.
And there's one in the back there. Say who you are and where you're from, and though statements are okay, questions are much more polite.
Not on? Now it's on. My name is Alfredo Araujo. I come from Barranquilla, and I thank you for your time here and would like to ask you, you just said that there's no economically viable solution yet for the storage at the grid level. Is there anything at the user level, at the home level?
Well, sure. You've got a laptop. You've got storage in your laptop. I presume, though, what you're talking about is there any storage mechanism that could supply your home?
Yes.
You can buy. The simple answer is maybe. You know, when we talk about, first of all, let's qualify the issue of whether something is economically viable or not, because it depends upon how valuable the service being provided by that storage is. So if you're running a hospital, for example, and you know the downside of no storage is that your patients die, then you're willing to pay an awful lot to put in storage. And you can buy it. You'll just pay for it. In the home, the best storage really is a generator that you put in place that you then turn on when your power goes off. So really what you're doing is you're storing it in gasoline or propane or whatever again. For small-scale storage, such as UPSs for your computer system, and actually, the UPS, which is dirt cheap, really, can be used for other things too, for very short periods of storage. If you lose your power for 10, 15 minutes, an uninterruptible power supply that you buy from your local computer hardware store can provide you with some reasonably good energy for that period of time. But for supplying your whole house with actual energy stored in electrical form, I don't see it. The closest thing may be, and this is again in the future, a fuel cell operated off of propane or
They're
gas.
signaling, alas, that our time is up. In all these discussions of energy, I'm always struck that we have an energy civilization that kind of works. I mean, maybe not as efficiently as we'd like, but it kind of works. And how we get from where we are now to the future that we know we need with some very promising technologies is not an easy question. And as I say, who pays for it isn't obvious either.
Who pays for it is the ultimate question. Yes, the technologies are there.
And John has been thinking deeply about this for years, and I thank him for his thoughts today.
My pleasure.
Thank you.
Thank you, Jason.